you to my lecture today. I want to believe this is 3032 class, right? Okay. Yeah. So from today, I promise I'm actually going to be recording, okay, and I'm going to be sharing the link to the recording after the lecture. So of course I provided the recording for yesterday, even though I did not record, I share what I did in the past. So you can actually check the canvas for access. Okay, so this is where the course starts. The one we did yesterday is just for you to have basic review of statistics, okay? So the course actually starts from here, okay? And want to introduce you to linear regression, okay? Today, June 4, and of course, the learning goal. Okay, you're going to understand the basic form of linear regression models. Then I'm going to distinguish between population regression model and a feeder regression model. So then lastly, we're going to have a way to interpret the coefficients of the linear regression models. Okay, before I get started, I actually told you the other time that we live in a stochastic environment and environment where there's a lot of variations. How do we take a decision that we are not going to regret? Like we want to understand our environment. So taking a decision that we're not going to regret actually requires or has having knowledge. And I remember I told you yesterday, knowledge is going to come from information we got. And information we actually come from, the data. And when you have your data, okay, when you collect your data, information you're looking for is not readily available. You need to actually use statistical model. Now, what is important in statistics generally is model. Okay, because before we can get meaningful information from data, then it means we have used an appropriate statistical model. But you know what we want to do today? We're going to apply model, but what do we want to apply model on? We actually want to know relationship between two variables. Okay, if I want to know relationship between two variables, okay, I want to investigate, then I'm actually going to use an appropriate statistical model. For instance, I want to know relationship between the length of stay in an hospital and income. I'm going to say that again. We want to look at the relationship between the length of stay in an hospital and income. Okay, if I'm assuming that relationship to be a straight line, okay, then what we want to do today is appropriate. What we want to do today is what we call linear regression model. We use linear regression model when we have an assumption that the relationship is going to be a straight line. Does that make sense? Okay, so and that is why today I'm actually going to walk you through that. Now, I want to tell you this. If I want to investigate relationship within statistical framework, the very first thing we normally do is to specify our model. I'm going to say that again. If I want to investigate relationship between variables, okay, the very first thing we do in terms of step is specification of model. Now, when we are specifying model, okay, the model we're going to specify could be linear model, okay, it could be linear, it could be quadratic, okay. There are different kind of models that we have. We don't just specify model, okay. We actually um have something that we need to do to be able to specify model. Now, let me tell you what we're going to do before you can specify model. You can generate what we call a scatter plot. Give me 1 second, if I can write this. Can you see that? Okay. You can generate scatter plots. Okay. And what do I mean by scatter plot? You can plot like the variables you are interested in. Okay, we're going to call one y. We're going to call the other x. The one that we call y is going to be the response variable. I remember the other time I said you want to look at the relationship between length of stay in hospital and income. The length of stay is going to be your response variable. The income is actually going to be the explanatory variable. So y is response, or we also call it dependent. X is explanatory variable. We also call it predator. Then we also call it independent. Okay, so y and x. So what we actually want to do is, if I want to know the kind of model I'm going to specify, then I need to generate a scatter plot. Generating a scatter plot is you having a diagrammatical plotting of y against x. Now, you're actually going to see whether the relationship is going to be a straight line or not. Okay, so now I believe you understand what we mean by variables now, right? Okay, in the model. And let me tell you this. Why are we studying relationship between them? Because sometimes if I have information about x, I can say something about y. If I have information about income, I can say something about the length of stay. Let me give you another example. In politics, if I want to look at the relationship between the percentage of votes received by a political party in 2020, or let me just say in 2016 and 2020. The 2016 is going to be X. 2020 is going to be Y. Okay. Now, why am I looking for why am I trying to characterize a relationship between them? Because if I know something about 2016, I can say something about 2020. Does that make sense? Okay. Now, take a look. I said sometime we use subscript to indicate different observation. Like you're actually going to see this. When you say y1, you can see 1 is a subscript, right? y1, y2 up to yn. Because if we want to investigate, we're going to take a sample, right? We're going to take a sample for y. We're going to take a sample for x, right? So that's how you say y1 up to yn. Okay. Now, when you see y1 up to yn, okay, this y1, y2, yn, we're talking about y observations. Okay, that's what we mean. Now, I want to talk about population regression model. When do we use regression model at all? Okay, we use regression model, okay, in study relationship. And I want to walk you through. We want to restrict ourselves to just 2 variables. We could study relationship in more than 2 variables, but right now we only want to start focusing on just 2 variables. Does that make sense? Just 2 variables. Okay. Now I want to specify population regression model. So, and under the regression model, because I'm only focusing on 2 variables, okay, and I'm focusing on 2 variables, then I'm going to call that simple. Simple means I'm only focusing on 2 variables. Linear now means I'm assuming a straight line. And that's why you say for simple linear regression, the population regression model is this. Please take notes. Okay? If I in assignment, if I ask you to state a population regression model for simple linear regression, this is what you're going to state for me. But you know what I want us to do now? I actually want to interpret each of these notations that you have here. This is a module. This is what I call module. You know, I told you that yesterday. I said module is a mathematical or statistical simplification of reality. This module is representing reality. Now, let's take a look at what we have in the module. In the module, we got, you can see Y, right? Can you see Y? Y here is actually the response variable, okay? X, okay? You can see you have an uppercase X, right? That very X represents the predictor or the explanatory variable. Now, you can see a lowercase s, right? A lowercase s is just a realized value within a capital X. Maybe, you know, what this guy is trying to say here, the expected value of response given the explanatory variable equal to a particular value can be written as what you see at the right hand side. Now, what you see at the right hand side, you've seen it before, you know, in high school. You know, take a look at this guy. You've seen that before in high school. The beta naught here is just the intercept. The beta 1 is the slope. Does that make sense? You remember equation of a straight line, right? Okay, so, but here in statistics, we call the beta naught and the beta 1 regression parameters. Okay, I want to believe the guy online can see what I write on the board, right? The guy online. Okay, so we actually call them regression parameters. The beta naught and the beta 1 together, they are collectively called regression parameters, beta naught and beta 1, but they also have their own specific name. Okay, we call beta naught intercept. Mathematicians call it intercept. We can also call beta naught regression constant. Regression constant. Then beta 1, we call that slope. Does that make sense? Now, what you are seeing now, okay, all of this that you're seeing right now, okay, all of this represent population regression model, okay, for simple linear regression, okay, population regression model for simple linear regression. And as you can see, expected value of y given s is trying to talk about the average value of the response given that the values of predictor equal to x. Does that make sense? That is what that is talking about. Now, if you understand that, I'm actually going to move. I'm going to move right now. Now, I want to talk about error. I need you to pay attention now. What is the essence of using a model? Essence of using a model is to depict reality. But I told you yesterday, model is not the same as reality. Okay? Model does not give us an exact reality. Why? Because there's always going to be error. Okay? There's always going to be error. What is error? The error now, what you are seeing now, the error now, is the difference between reality and model. Okay? There's always going to be a gap. I want to use a model to depict reality, but the best model will never give me an exact characterization of reality. It's not going to be possible. There's always going to be what I'm going to call a sacrifice to make. There's going to be lots of information. So error, what you are seeing on the board now, E, error equal Y. What is Y? Y in this case is observed. What you observe, like what happened in reality. Then the expectation of Y given S is what your model suggests. Does that make sense? You know, expectation of Y given S is what your model suggests about reality. Y is the reality itself. then I said error can never be zero because there's always going to be a gap between model and reality. Does that make sense? We acknowledge that in statistics, there's going to be an error. But what we normally try to do is to look for a way to minimize the error. But no matter how we minimize it, it can never be zero. There's always going to be a gap. Any question about that? Please, I want you to pay attention to notations. I told you the other time, the reason why statistics may be difficult, mathematics may be difficult is because you don't relate the notations. Okay? Now, if you understand that now what is the significance of error in a model? Take a look at that. It accounts for the variation in y that cannot be explained by x. We want to use x to explain y using a model. Because our model is not perfect, then S cannot explain everything about Y. There's still going to be something, okay? And that is why we normally call that unexplained variation. Okay, let me put it to you like this. We have a total variation around the response. X will only explain some, and others will be unexplained by X. Does that make sense? Okay. Now, and that was why we said the error that we're talking about does not depend on X. What is error in actual sense? Okay. The other time I actually used politics, I said I want to look at the relationship between the percentage of votes received by, let me just say in the United States, by a Republican candidate in 2016 and the percentage received by the Republican candidate in 2020. Of course, in 2016 was President Trump, right? Former President Trump, right? In 2020, also former President Trump. So now what we're trying to say by error here, it is not only, if I want to explain what former President Trump got in 2020, okay, it is not only what he got in 2016 that we explain that. We could have other factor that explain 2020 and other factor that our model don't talk about is what we call error. Does that make sense? Okay, it's unobserved. Okay, do you understand that? Okay, now the next thing I want to do now, and I want to have a model. You know, I just show you the population regression model. But you know what? I actually want to have a model that will incorporate the error. And that is now making Y, the response variable, to be random. Because of the fact that I incorporated the error, because there's always going to be error. I told you the other time, when you're using a model cannot give us an exact characterization of reality. Now, because of that, I'm going to tell you this. Take a look at this guy now. This guy, the whole of that is what we call deterministic part of a model. Deterministic part. Then the other part error is what we call the random part. Statistical model is a combination of a deterministic part and a random part. Does that make sense to you now? Now, when you now focus on that, you're actually going to see that this guy is this guy that we also call this guy. And that was why you see that I said this guy is this guy. Does that make sense? Any question? Do not hide your feelings, okay? Make sure you ask question in case you got one. Okay, now the next thing I'm actually the guy online, can you confirm if he has are you getting what I've been explaining? You are muted. I need you to unmute. Can you hear me, the person online? Okay, I think the chat came in. Oh, the person said yes. Okay, thank you for that. Okay, now I want to move right now. Okay, I want to move right now. let me clean this first. Okay, then before moving. Now, what I showed you before, we call them population regression model. Why do we call them population regression model? If I want to, if I'm looking at the relationship between variables, two variables, and I want to make use of all the data available, like the whole population. But this is not realistic. Okay. What do we normally do in research? We normally take a sample, right? We don't have resources to study uh, every element in the population. Now, if we take a sample, then we're going to move from population regression model to fitted. Do you see fitted? There's a difference between fitted regression model and a population regression model. Okay, the population regression model is applicable to population of data, like everything. But the fitted, the fitted is going to have a cap. Take a look at the specification now. You can see a cap, right, on each of that. Y cap, you know what Y cap means? Y cap means predicted Y, predicted response. There's a difference between having Y. There's a difference between, okay, as you can see here, there's a difference between this Y and the Y that with a cap. The Y without a cap is more or less talking about reality. The Y with a cap is your model that will give estimated reality. Estimated reality. So that's a Y with a cap. Y without a cap is the original response. What happened in reality? Okay, now when you take a look at this is a fitted regression model. The beta knot is going to have a cap. The beta knot having a cap, you know what I mean? Estimate of beta knot. Okay, it means estimate. Why are we using estimate? Okay, why are we using estimate? Because sample is involved. Okay, when a sample is when you are using few instead of the whole elements in the population, then whatever we're going to be doing is going to be estimation. Does that make sense? So the beta knot cap is an estimate of a constant, of a regression constant, or estimate of intercept. Then the beta 1 cap is an estimate of the slope. Okay. Now the only thing here without a cap is x. You know why x does not have a cap? Because we believe that x is fixed. Because x is an explanatory variable, we've already secured x. We have information about x, but what we want to do is to use the information about x to figure out something about y. And that's why x doesn't have a cap. Does that make sense? Okay. Now, when you are talking about population and you want to look at the distance between reality and and what the models say, that distance we normally call it error. But if you are working with sample, okay, we don't call the distance error, we call the distance residual. Can you see the difference now? The two of them has to, in the actual sense, let me tell you, in the actual sense, the residual and error may mean the same thing, but except that we call it error when we're dealing with the population, we call it residual when we're dealing with a sample. Does that make sense? And the residual here now is a difference between the observed response and the predicted response. The Y cap is a predicted response. Okay. And where is the predicted response coming from? The predicted response is coming from your model. Oh, maybe I already know my beta knot cap. I have my beta 1 cap, and I know the values of S. Can I make a prediction about the values of Y? So the Y cap actually comes from the model. Is there any question here about the difference between error and residual? Now, I wanted to take a look at this again. Error does not have a cap. You see E? Does it have a cap? No. Error doesn't have a cap. But here, residual has a cap. And let me tell you this. Residual is an estimate of error. That is why you see having a cap. Any question? Is there any question at this time before moving forward? Any question? You enjoying the class, right? Do you understand it? Do you not hide your feeling? The moment you don't understand, please ask me question. Okay, so like I said, residual is the difference between the observed Y and, a Y curve. Okay, now I want to move right now. I told you the other time, if you really want to know whether you should specify a linear relationship, you actually need to generate a scatter plot. Okay? And what do I mean by generating a scatter plot is having a diagrammatical plotting of Y against X. Okay, when you have a diagrammatical plotting of Y against X, I want you to take a look at what you are seeing right now. Let me see if I have a further information here. Okay, give me 1 second. Now, I need you to take a look at the dotted line in blue and the solid line. Okay, the solid line is actually giving expected value of, it's actually giving the 0.3s. And the other one is, now what I'm trying to say here is here, we use sample, but here we use the entire data set. That's it. So the one where we use the entire data set is a population regression model. The one we make use of the sample is a fitted regression model. Does that make sense? Okay, where we use sample, we call that fitted regression model. And that was why you see I said the fitted model based on one sample data. Okay, now what am I trying to showcase here? The very first one was we make use of one sample data, but in the other one, we use so many. Of course, we expect a deviation, okay, between the two. When we use just one sample data and when you use so many, okay, and that is what you can actually see here. Okay, there's a deviation. Okay, and I said most of the time we don't have. Now let me tell you this. Do you know the one that is appropriate, right? The one that is appropriate is actually the population one. But let me tell you, in research, even though we're looking for efficiency, but we also want to reduce costs. Okay, when you study more, you're actually going to spend more. And because of that, what we normally want to do is we're actually going to consider choosing a large sample. Does that make sense? Because the more sample you take, the more you are very close to the truth. Does that make sense? Okay. And that was why I said here, I said most of the time, we don't have access to the entire population. Even if we have access, we don't have resources to study everybody. Does that make sense? And how are we going to do it? But we want to draw a conclusion about population. We don't have access to study everybody, but we want to draw a conclusion about everybody. Then it means if we are taking a sample from the population, then that sample should be large, and not only then it should also be a random. I told you yesterday, you can when you choose a random sample, then you can generalize. Does that make sense? But if you don't choose a random sample, there's no way we can generalize, because the idea in statistics is how can I use the knowledge, my knowledge of few, to make a judgment about the entire, about the whole thing. Does that make sense? Okay. Now, please, I need you to be focused here now. One major goal of statistics is making inference. You know what we call inference? Inference means making decision, making judgment. And most of the time, if we want to make judgment, we don't study everybody. So how are we going to do it? Draw a sample. with sometimes far less individual than the entire population. Then given the potential error in the sample information, because let me tell you, the reason why our model cannot give us exact characterization of reality is because we normally take sample, and sample comes with error. Does that make sense? Samples come with errors. Okay, what can we conclude about the trend in the broader population? Okay, so what we're going to do, we're going to choose a sample in such a way that we'll be able to manage the error. We'll be able to minimize the error. And we got conditions, assumptions. That's what we're going to do tomorrow. How many of you have seen the lecture note for tomorrow? I've already published that on Canvas. Okay. Oh, you've not been checking Canvas. I think I've done. Did you see lecture for today, right? Oh, okay. Maybe I'm going to check. Okay, now take a look at this. Please take a look at this. If I know this, where do we use this? On the sample, right? This is a fitted. If I know this, what can I say? What do I want to know? This is what I want to know. That guy has to do with population. That's a population regression model. We don't have resources. This is exactly what we want to know initially. But this is what we end up knowing. That is what we want to know. This is what we end up knowing. The other guy has to do with the population. This is a fitted that has to do with the sample. Okay. Now, I want to go into an example. The other time I used politics, but this time around, I want us to go into factory production. Okay. Now, in this company, you know what we want to know. Okay. We actually want to look at the relationship between run time and the size of production. Okay. If we produce 20, what is the run time? Okay. And in this company, we don't have access to all data. What do? We only choose 20. Can you see that? N equal to 20. We only choose 20. Okay. When you choose few, then that is a sample. So if you really want to use a model here, a simple linear regression model here, you're actually going to use a fitted. Does that make sense? Now I'm going to show you the data now. Okay. Oh my God. This is the first 10 data. Okay. For, choosing 20 means we're going to have 20 cases, right? Okay. And the 20 cases was choosing randomly from, because I'm not going to say it is not only 20 times they work in this company, they work. So we only choose 20. Now, the first case, when the run size is 175, that took them 195 run time. Now, these are available data. Now, if we want to have a sense of a model that you're actually going to specify, we need to generate a scatter plot. This is like plotting Y against X. Yeah, I call Y runs time, okay? And X is the production quantity, okay? And why is it called a scatter plot, okay? Even though it is not until we have a perfect straight line, we can never have a perfect straight line. There's going to be some point that are scattered away. The only thing we're going to be looking for is a line of best fit, okay? Now, take a look at that. Now, in this course, you're actually going to be having a lab where the TA is going to walk you through this is a code right now. Okay. R code, you're actually going to be using our software. Like on this Friday now, the TA is going to walk you through how this can be implemented in R. Now, if you take a look at this is a code. This is a code to my data, to the data. The data name is production. Okay. That is, this very code here is, the data is actually online. Okay. And if you copy, you can see HTTP, right? If you copy this into R, okay, and you click and you write production, the data will be displayed. Does that make sense? Now, head equal to C. So if you take a look at that, that's a code to import your data. Like TA is going to walk you through how to import your data, whether from online, whether from spreadsheet, and so on like that. You're going to do that in the lab. Now, I need you to pay attention now. How do I run my module? Like the fitted. In a fitted module, okay, we want to get beta naught and the beta one, right? Okay, now take a look at this guy. If you write this guy mode, and you write LM means linear module, they have to be lowercase. The moment you actually write uppercase it's not going to run. It's going to display error. Does that make sense? Now, the very first thing you're going to write, what you're going to write first is your response variable. When we started, we call run times Y. Okay, response variable. I'm going to show you right now. Or do you see that Y is a runs time? Okay, the examiner, we're going to give you what Y represent, what X represent. Does that make sense? So in the hero code, okay, you always going to write the response first. Then you write this sign. Then the run size here is the X. That's what represent the X. Then you need to tell us the data that you actually want to use. Initially, we've already imported the data, which is production. Can you see data equal production? Then after that, which means this very code now is to fit a linear model. Okay. Now, if you want your result to be displayed, then you're going to move to this. Here I use MOD to represent all of that. Then I'm going to say summary of MOD. And that will display result. I'm going to show you what it's going to display now. You're going to have this displayed. This is what you're going to have. Okay? That is what you're going to have in displayed. There's a lot of information here. A lot of information here. Okay? That I'm actually going to walk you with. But let me just say what we need right now. Let's say, for instance, I actually ask you to obtain a fitted regression model. If you want to obtain a fitted regression model, okay, it is y cap, okay, y cap equal, okay, beta naught cap, okay, beta naught cap plus beta 1 cap x, okay. If I want to rewrite that, my y cap is a runtime. You can see when I write runtime, I put a cap, but don't put a cap on run size. Run size is x. We don't put a cap on x. Okay, now what is going to be my beta now? What is going to be my beta 1? Then you're going to go to the estimate. Do you see estimate? Okay, you see this guy now? That is for the intercept. And this guy is a slope. And that is what I plug in. Can you see that? Any question about this? Okay, we actually run, we implement the data using our software, and from the output display, then we're able to extract the slope and the intercept. Now the module now this is the module now. That's a feeder module. If I only want to write it in a mathematical form, it's just going to be this guy. But if I want to be specific, and we need you to be specific, because you need to tell us what y cap represents. You can see that. Is there any question about this? Any question about this? Okay, as time goes on, I'm still going to tell you the meaning of standard error, t value, p value, and so on like that. But what we need today is just the estimate. Now you know how to extract the estimate, right? Okay, the next thing we want to do right now, can we provide an interpretation to what we got? There are two things we're going to interpret. This is a model, right? Okay, this is a model, mathematical form. Okay, how do we interpret intercept mathematically? when s equal to 0, okay, your y-intercept will be the values of y when s equal to 0. In this case, when s equal to 0, y will be 149.75, okay? And the interpretation is going to be, I said the values of y will be, what is y cap? The y cap means average. I'm going to take you back so that you'll be able to see. Y cap actually means average. Can you see that? Y cap is average is expectation. Does that make sense? So if I want to interpret y-intercept, I'm actually going to say when s equal to 0, then the values of y on average. Does that make sense? When s equal to 0, the values of y on average. Okay? So here now, okay, to answer the question. So let me just quickly prove that. Okay, when s equal to 0, now I need you to pay attention. In interpretation, we have two forms of interpretation. We have the basic one. The basic one is mathematical one. And we have the one according to the context, like the question. Now, I want to interpret this guy now. Okay? If I want to go by basic, when s equal to 0, that guy is the values of y on average. But if I want to go by context, I will have to mention what y represents in the context and what s. Look at what I said. When we produce 0 products, you can see it's in the context now. That is no longer mathematical interpretation. So when we produce 0 products, it takes 149.74 minutes on average. What is it meaning? We have not produced. We spend time. Oh, that may be a setup time. In a company, before they produce, they're going to have a setup time, right? The time of putting equipment in place. That makes sense. Does that make sense? That is what we mean here. Is there anyone who doesn't understand that interpretation for both basic and context? Okay, now the next interpretation is the slope. Then I'm going to first start with basic one. In the basic one, I'm going to be talking about mathematical interpretation, y and s. So I'm going to say when s increase by 1 unit, okay, the value of y, the values of y could increase or decrease depending on the slope, depending on what you see here. Depending on the sign. When the slope is positive, you mention increase. When the slope is negative, you mention decrease. Okay, so the basic interpretation now is when s increases by 1 unit, you're always going to say that. When s increases by 1 unit, the values of y increases by 0.26 on average. You must mention average at all time. Whether you are interpreting the intercept, you're going to mention on average. Whether you are interpreting the slope, you're going to mention on average. Does that make sense? Okay, now what about in the context? Okay, in the context now, when we increase the size by 1 product, don't forget, okay, the production quantity is X. When we increase it by 1 product, then the running time increases by 0.26 minutes on average. This is going to make sense, right? To the research world. Like, if you want to put into consideration the context, okay, don't just give basic mathematical interpretation, but also give the contextual interpretation. Does that make sense? Okay. Oh my God. That is going to be the end of today's lecture. Do you have any question before I go today? Any question? Do you have any question? Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.